first I'll wrap up this and then go into wide area monitoring and control. And then I have an example from large-scale analysis. But just want to emphasize that what we have talked about today is really in a result of the solution to the linear differential equations. And since we now have talked, just had examples where we had just only one mode. I mean, it was fairly simple because we had had this type of system plus something driving it, and then the derivative, of course, and then you know that the solution to that in time domain is something, some constant, and when lambda is sigma plus minus j omega, of course, this comes down to plus some angle. So this is easy when you have just one mode, but when you have a multi-machine mode, it's very easy to extend this principle to that, because we know that, okay, for the system we did the transformation to with the eigenvector, so that essentially the solution to this x of t is derived from this. It's if this is number 1, for example, x number 1 is 1 1 set 1 plus 1 n set n, and then you see that each of these z's is governed by one eigenvalue only, so that it becomes 1 1 lambda 1 plus v1 to lambda 2t plus so you see that the final solution to any state variables is a linear combination of the modes, the eigenvectors, and the observability, or sort of the amplitude of these elements are determined by the eigenvector. So that sort of is an attempt to describe the mathematical background for this, which I guess you know. So therefore, and in a large system, the solution will be a linear combination of many such modes, both complex modes and real modes, and hopefully they're all with a negative real parts, or else the system is unstable. Okay, we have looked into these methods then. Mainly we looked at eigenvalues and observability factors. You will also very often encounter analysis that have used participation factors or transfer function residues, which is more or less a combination of observability factors and controllability indicators. If you have a large power system, and I'll show you now an example from analysis of the Nordic power system with something like 1,000 generators. And there you will, of course, if you try to plot all the eigenvalues, if you are able to do that, you will see them all over. Hopefully not in the right half plane, but they will be all over here. And then, of course, it relates to many things. It could be fast controller modes, relatively fast electrical modes. There are slow modes due to turbines, for example, turbine dynamics. And there are these modes here that I say these are the electromechanical modes that sort of govern the power oscillations and so on. And if we zoom in on those, you see that they're all scattered here in the range from, let's say, 0.23 hertz up to 2-3 hertz. And these are the ones that we are concerned about. That are closest to the real axis with less damping. So, and we also looked at how we could depict those mode shapes with phasors, so that you can have an idea which generator are oscillating in phase or which are oscillating against others. That came from the sort of the complex. If you draw the vectors of the complex number, you get that. And then you could, based on that, those drawings, you could say you could characterize the modes. If there are just one eigenvector that is peaking out, then it's probably just one machine that is poorly controlled or not well adjusted. So it's a local mode, one machine that swing against the rest of the system. Then you could have some modes where you have a few peaking out. In this case, it's one generator here that oscillates against two others. Sort of local phenomena, but still more than one machine involved. And then you have the inter-area modes where you have many generators maybe oscillating in phase against the rest of the system or against a group of other generators. So, before I go to the example, just summarize. Linear analysis is a powerful tool for stability assessment on controller design, because you have the numerical methods from linear algebra that you can utilize. But still be aware that this is not a tool to assess the response to large disturbances. It's about analyzing or identifying the nature of the system. When it comes to larger disturbance, the non-linear effects become more important, and therefore you need to do transient simulations to verify your results in a way. Okay, use a few minutes on this example. Again, we talked about yesterday, or was it on Monday probably, that in the Nordic system, this is a picture of southern Norway, the border to Sweden. There is a high focus on the power transmission corridor between Norway and Sweden, because there is a demand from the power market to export hydropower from west to east, you might say. Also from the west to the south through the HVDC links to Denmark and Germany and to the Netherlands. Germany link is not ready yet, but it's coming. But the transfer capacity is as limited as I explained. You could have thermal capacity limits, voltage stability, angle stability, and everything. So we need to analyze what is the limits. And this refers to a modal analysis, a small signal analysis of the system. What we find from doing a eigenvalue analysis is that we have modes around 0.3 hertz. We have a mode at 0.5 hertz approximately, and we have several modes at higher frequency. Now, the two that are of interest in this study that we will see later are these two at 0.3 and 0.5 hertz. And in order to classify those, we do a modal analysis. And if you look at the 0.33 hertz on this huge model and plot the eigenvectors, the elements of the eigenvectors related to speed of the generators, we see that we have a bunch of eigenvectors that point in the same directions, or eigenvector elements, I should say. It's not that they are not. They are complex numbers. They are elements in the eigenvector. They point in the same direction, and it turns out that they are all related to generators in the Finnish grid. So, I mean, I don't expect that you are very, very well known about the geography of the Nordic countries, but let me try to draw it. We have this is Norway, this is Sweden, this is Finland, and this is the Baltic Sea. This is sea, and Russia out here, and these are our corridor about here. But there's also sort of a corridor up north to Finland. So you might say that Finland is at the totally opposite end of the power system. Therefore, you have low frequency oscillation between them. And the Finnish generators are sort of usually in opposite phase to the rest of the system at 0.33 hertz. If we look at the 0.5 hertz mode, we see a little bit more complex pattern, but it is clear that all the generators in southern Norway is in phase at that frequency, and they are almost in opposite phase to southern Sweden and Denmark. Denmark being down here, of course. So you might say that the 0.3 hertz mode is like that, and the 0.5 hertz mode is like that. If you think of generators as springs at the end of the system. And then the other modes, they are more of local nature, and this one is in northern Norway, and another one that is some oscillation between areas in southwestern Norway. So the conclusion is that the 0.3 hertz mode is an inter-area mode. Main observability is in Finland, southern Norway. 0.5 hertz mode is also an inter-area mode. Main observation is in Sweden. I should also say that western Denmark, eastern Denmark, I mean, and southern Norway. The other are a little bit more local. or they are fairly well damped. So what is the issue now? When we're trying to assess this, we need to sort of, or to assess the transfer limits, we need to do some analysis. And this will sort of is one side of having analysis. Now we're talking about computer analysis. Later we will see that what we can do also online with phasor measurements. But what you want to do then to assess where is the limit is to sort of increase the transfer in some natural way on the corridor and see where the eigenvalues move. And what we see is that the 0.5 Hertz mode stays at approximately the same relative damping when we increase. But what we see when we come to a certain point is that the 0.3 Hertz mode starts to drop in damping. And at some point it's critically damped. And in this case I say, okay, the damping here is down to 3%. So perhaps this is our limit. Stability limit, 2,200 megawatts. So that is one use of this. But you see the complexity because there's more than one mode. So it's important to sort of track all the relevant modes. You could verify that by simulation. By intact network, it's no problem. You see the oscillations, and you can recognize the frequency. But when you do sort of the n-1 test, then you see that when it becomes critical, in the start here, there are 2 seconds between the maximum of the power oscillations. So this clearly is the 0.5 Hertz mode we see here. But when the power flow is increased, you see that this is more like 3 seconds. Or even at some point more when it starts to get transient and stable. But up here, you see it's a 0.3 Hertz mode. So it verifies that you should not go about 2,200 megawatt at least. So from this we can draw some sort of practical experience. We can use this as a criteria and guidelines for determination of stability limits that we can use in operation planning. That is to set the limits for the power operator or for the power market. In this case, we tested this also for the transient simulation and found a fairly good correspondence. But of course, stability limits are not the only parameters that determines the transfer limit, so we need to look at the others as well. When it comes to this analysis, we used a special program for that. In this case, we used the program called PACTIN, which is a problem developed by the Brazilians, the research center CEPEL in Rio de Janeiro. But I mean, if you some kind have some mean have the linearized system model, you could do this very easily also in MATLAB or other programs. Power Factory has a fairly good tool for small signal analysis. So I can demonstrate that later. In PSSC, there are some methods available, but you could also use other methods, such as the Prony method, to identify critical modes. An example of a Prony analysis is here. And I'll also come back to Prony analysis later when we talk about PMU applications. The Prony methods is based on that there has been a kind of disturbance. So you have an oscillation that has a certain ring down, as we would call it. And I mean, just after a disturbance, you would expect that there are several modes involved, so non-linearities involved. But basically, if you have one critical mode, you're able to catch that if you look into the ring down or the exponential response, damped response of that signal. So it's really about computing or making a best fit of an exponentially damped sinusoidal signal to this and extract the eigenfrequency and damping of that signal. That is the Prony method, so that you try to try to fit such a function to your signal and obtain the sigma and the omega and the theta. If you have two signals, you could also sort of estimate the mode shapes by comparing the phase shift and the amplitude of the signal. So, I mean, PSSE, for example, has a tool for that. It's not possible to see, but if you go closer, you can see the ring down here, and how you select the window, and you get a number. You get sort of the best estimate of the eigenvalues for that signal. So that was more or less the introduction. Development trends and future challenges and possibilities. I think that we can wait with that to until Friday. There's not that much, but this was the introduction. Say 2.5 days of introduction, but it's the basis for everything we do when it comes to wide area monitoring and control. So I think it's worthwhile to spend time on that. Do you have any question before I continue? Yeah? Yeah.
So how much this would increase
The damping. Well, that is yeah. It's always a discussion how much you need. What you need to take into account is that you need a certain margin in the contingency case. So if you are simulating the worst contingency and you have 5%, then you're good, I would say. Maybe also 3%. Maybe 2% as well, as long as it's the worst contingency. But that is important, that you're simulating the worst contingency case and not the sort of the normal intact grid, because then you will probably have more than, you probably need more than 5%. But in the case where you have already lost a critical line or something, then maybe 3%.
In the previous slides, you have told, you have seen previously that the local mode was in the range of 0.551.
Yeah.
Generally, the inter-area mode is between 0.1 to 1
Yeah.
hertz, and 1 to 3 hertz is the local mode that in a multi-mode or synthetic mode.
Good question. You talked about this one. Yeah. Yes. Yeah, of course. I mean, that is always the issue with such analysis, that you never know exactly if your models are validated. So in this case, this is a local problem, and it has to be dealt with locally. I mean, you cannot. It's more or less independent on how much power you transfer in on this corridor, because this is one generator or some generator that are locked on a long line within a valley, far from people, something like that. So it has to be dealt with. You have to know the system. You have to deal with it locally. Was that an answer? Somehow? Okay. We can keep on a little while before we take a break. So the plan is now that I will give you an overview of the subject related to wide area monitoring and application of phasor measurement units. And then, as time allows, we will go a little bit more in detail into some of the application that is relevant, that has been developed, show some examples of tools that we have implemented. And that will be today and tomorrow. Maybe tomorrow afternoon or Friday morning, I'll talk a little bit also about multi-terminal HVDC and the controls. It's relevant, but I mean, when we talk about DC, control of DC networks, phasors are not that interesting anymore, since the frequency is usually 0. But some relevant sort of ideas can be brought up by that as well. So this is for those of you who happened to be at the conference here for two years ago, they will have seen quite a lot of this before. It's an introduction to the subject. A little bit on motivation for wide area monitoring. Something on a little bit general on measurement, experiences, and application. A little bit on what we sort of early on started with, voltage stability assessment, power oscillation monitoring, and estimation of characteristic responses in the power system. Then a little bit on the possibilities of wide area control. I will also show an example on wide area, what we could call wide area protection tomorrow, or yeah, tomorrow will that be, I think. And some examples here are from research collaboration that we have had in the Nordic countries, and also together with MNNIT here with Professor Kjetil. So again, a little bit on motivations. Again, what we are facing, the trends that I talked about also on Monday, that we are facing faster and larger changes in the operation of the power system. We see more variability and more uncertainty. These are two different things. The variability may very well be predictable. Then it is a different challenge from when the variability is due to uncertainties, or that you don't know where things vary. In any case, you have less predictability, and thereby the consequence is that you have less time to take actions, also to make decisions when you are in the control center. That is why the operators need new tools, and that is why we are working on this. So in order to approach the need for to take faster decision based on uncertainty. We need more real-time information. We should need higher resolution of our measurements, and synchronized measurements is one of these things. And there's also that we see clearly more need for automatic control, because at a certain point things cannot be managed by the operators manually. You need automation. So in that sense, the new technology that is put forward by phaser measurement units, for example, is interesting. So if you look at the, let's say, the evolution of the control room and the work environment for operators, you see the development from the time when they had analog instruments to where something was digitized. I would say in the changing from the analog instruments into the digital, they lost some information, I think, because with the analog instrument you could easily see power oscillation and how things work. Having the information in a digital form, you don't really do that. But that was the future, digital instruments. And then you got sort of what we should call now fairly modern SCADA system with a lot of information, large screens. You had EMS software, energy management system, which could do some simple analysis based on state estimation. You have state estimators which could provide you with a power flow solution, and you could do, for example, contingency analysis. You could check how much reactive power you needed to keep the voltage at a good level and so on. So very much this is where we are now, but we're heading into this, where we are introducing into the SCADA AMS system also phaser measurements. So today we are at the stage that we are searching for good application of PMUs in monitoring of specific conditions. And those are what we will call the wide area monitoring systems. How do we utilize the enhanced information in the control room given today's technology? And in the research we need to look into the possibilities of the future. And what we are sort of envisioning there is more sort of in terms of live simulators, autopilots, things that can tell us immediately what is wrong, point to where we need to do controls, etc. So this is the sort of what you have to envision when you are working in this area now. How can this be utilized in the future, where we have all this information, we have communication, we can measure both things, we can control many things. That's the motivation. How do we get to the future control center with all this live information that can be sort of it's a way, in a way it is from going from black and white television to nowadays high density HDMI world, it's another dimension to anything. The resolution is much higher. Okay, just again, just to say a few words about our challenges. Here's the Scandinavian or Nordic system again. In Norway, we have control centers in Oslo, the capital, and also one up here in the far north. And they are controlling the entire grid. The distance here is 2,000, more than 2,000 kilometers. Fairly long distance. Low populations in the northern areas, but the lines are long, so it's dynamic system. I said this, I showed you before, so I won't bother you with this again, but it's about monitoring with the aim of improving the stability limits. So we need to determine the capacity limits. We need to be able to monitor them in real time and then enforce the power transfer limits online, or even improve them with better controls. And the background for this is as I have been touching upon, that traditional SCADA EMS is rather slow. It's focused on steady state. You have updates with different sampling rates. Could be maybe from minutes somewhere up to maybe down to 1 second or something. But it's not synchronized, and the measurements are coming in when they're available. So that must have focus on the steady state. But as we have seen, the power dynamics can be much faster than 1 second. So we need an enhanced information that is available with phasor measurement units. So you could use that with respect to determining the limits. You could, for example, use phasor measurement for state estimation. You use wide area monitoring tools to manage to monitor your limits, or to know your limits. And you can develop wide area control technology to hopefully increase the limits. So that's the starting point. That's the possibilities that we see and the challenges. So what can we do then? So first, I guess since you went to this course, that you all sort of know what a phasor is, but still I always take it with me because I know that many people talk about PMUs without knowing what a phasor is, and that's not good. So, but we are used to the concept of phasor from our calculation when it comes to AC grids, right? So, but in principle, the phasor concept is just a way of representing a time-varying signal. A time-varying signal has an amplitude, and it has a phase angle with respect to something. You can always discuss that what the reference angle is, and you can vary that, but you have to have a reference for angles. And with that sort of reference, you can draw the phasor as a complex number with an amplitude and phase angle. But the interesting thing is that if you have two measurements, of course, or more, because then you're able to measure the phase angle difference between the phasors. And that is the strength of PMUs, of course. That the measurements are synchronized so that you can measure the phase angle correctly or with a good accuracy to place them in the same phasor diagram, even though they might be hundreds of kilometers apart. That is done by GPS or corresponding synchronization. And then one would ask, why do we care so much about these phase angles? And I think you have seen that from the first days here, that these phase angles, they matters a lot in ACU systems. And the simplest way of sort of explaining that is to just look at the power transfer on a AC line, where actually the power flow is more or less proportional to the voltage angle difference between the two nodes. So two large angles is critical. And the ability to measure those angles give you better information than just measuring voltage and current. Even though you could, of course, what you do partly today is that you estimate the voltage angle by the state estimator, because you are able to measure voltage and current, so you can compute power. But still, that is not within the resolution, so that you can capture dynamics in a good way. So that is the definition. The phasor measurement unit then is in principle like this. You get your analog inputs, voltages. See, I have forgot to translate this. Voltage or current, three-phase or single-phase. Depends what you want to do. You need to condition the signal, of course, filter, and you need the analog to digital conversion. And then the point is that the measurements are synchronized through a phase-locked oscillator that is being triggered by a GPS signal, so that you have the synchronization done there. And then there is a processing, basically a kind of Fourier transform-like processing to get the phasors out. You could say, in principle, normally one phasor per period. So resolution of the phasor measurements could be up to 50 samples per second. Sometimes also it can go up to 100. But I would say that the definition of a phasor in less than one period, it's a little bit fussy to me, but okay, you can do it. Then of course the good thing is that what you need to transmit or to stream out to the system is very much less than if you had to transmit the original samples of currents and voltages. So a phasor measurement unit has usually has an Ethernet port, and these are following the Internet protocol, as far as I know. I'm not good at communication, so yeah. What is the difference? Oh, no, it's what it is? Modem. Yeah. Oh, yeah, it's, well, this is mainly to say that there is a communication right. So, as far as I know, what I have seen on the PMUs that I have seen, it says an Ethernet plug, right? So it's not an antenna. The GPS antenna is there. This is the communication. Maybe I should change the symbol. Make it an Ethernet port or something, because that's what it usually is. Yeah. The point is that you communicate. You stream the values out of this, the phasors. Is that okay? Maybe I should change it. So that's how it goes. 50 Hertz signal input, 1 phasor output. And then you would normally send the measurements to what we'll call a phasor data concentrator, which is another computer, perhaps connected to a database or a storage, so that you align the phasors from all the PMUs in a synchronous way. So if you, I mean, they have an IP address or something, 241, and they stream the data, all of them, into a PDC. And this will align the data with a time, phasor 1, phasor 2, phasor 3, and the variables here. 2, 3, 4, 2, 6, 9, for all the PDC. So if you are and then this could communicate again with another PDC in another country that has other PMUs coming in. Yeah.
How the reference is used?
The reference, yes. The reference is that time, actually. The reference is, I think it's called UTC, which is fairly relevant with the Greenwich Middle Time. And it's so that the reference to what we measure is a 50 Hertz signal, perfectly 50 Hertz, with some reference to the clock, if you understand. What exactly where they put the starting point is, I don't know, but it's usually the phasors are referred. I mean, again, it's up to they don't do this in the US, of course, where they have 60 Hertz. Then they have the 60 Hertz reference. But the point is that it's all referred to a time with accuracy of 1 microsecond. And where this started, I don't know, but this is the reference phasor. So if you have another frequency, if you have another phasor that have another frequency, of course, then it would the phaser would take, if the frequency is 49.9 hertz, it would take 10 seconds for the phaser to do one circle in a way. I'll see if I can get contact with the PMU so that we can show it on screen. Yeah, this was to show sort of what it is. I mean, sometimes in power station or so, the PMUs would usually be part of the protection system. So it will be one box in the cabinet of where you have the protection system. What we have in our lab are PMUs that are implemented on the hardware of National Instruments. So this is basically what's called a compact REO chassis, where we have partly implemented the software ourselves, and there's also open software available. National Instruments has their own software you can also use in LabVIEW. So in this you have, this is the GPS receiver, so you have an antenna plug. These are analog inputs for currents, analog inputs for voltages, and here you have the Ethernet unit with the Ethernet plug, and these are some other ports. Serial port here. I don't know. That's basically what it is, right? It's analog to digital converters, antenna, communication, and a processor. Yeah. The picture is a little bit better here. But you can recognize the Ethernet port, serial port, analog inputs, and antenna. So I think I have talked for an hour. Maybe we should take a break before we continue now. I think that's a good idea. I think so. 15-minute break.